Okay, let's start.
Okay, so hello everybody, and now we are going to present to you the project that we have worked on. First of all, let me introduce you the people that we have worked on it. Ferran, Jordi, myself, Melania, and as advisor, Kevin. So yes, this is a similarity engine on clothing dataset. So yeah, retrieval engine. So what are the motivations for this project? Basically, we wanted to give a better option to people that, for example, check that there's a cloth that they have interest. Usually the thing that you have to do is just input the characteristics that you see on the cloth, like, I don't know, brand if you know, color, texture, but it's way easier if you just take a photo, put it in a retrieval engine, and it will give you a recommendation on similar clothes. So yes, this is our motivation. The goals for this project is to build an entire system end to end. So meaning that we have front end where the user can input the image that they want to see similar clothes. This then will be passed through an API to pass it to the backend, so to the neural network that is the one that has the retrieval engine, and then give this top 5, top 10, top 15. You will see it later that there's like different options. And yeah, check the similar clothes to the one that you have input. Yeah, so the proposal basically very similar to what, yeah, to the goal of the project. So build an end-to-end product where we input this image. It can be ideally in the future would be maybe taking a photo from an app, but for now it's inputting an image, and then after getting the best result thanks to the retrieval engine, it will output in the same application the top 10, top 15 similar clothes to the one that you have included. And yeah, now back to Ferran.
Yes, thanks. So I'll talk about the neural architecture. Basically, we've evaluated several of the different feature extractors that exist. Well, we selected these ones, the VG16, the ResNet 50, and the ones that you can see here. So our objective is to take the features of each of our database image, so it's easy to compare how the image that it's arriving from the front end, it's similar to the features of the ones that we have in the database. So in order to make it efficient, we perform a dimension reduction on the features that are outputted by the different models. And finally, some normalization that makes easier for the engine to work efficiently and also to achieve better results. So to achieve these results and our system, we need some models that at the end we train as it are, but also we use it to transfer learning and adapt it to our database to make it better. So to evaluate our retrieval engine, we use several metrics like the relevance of the images that are retrieved, the speed that we achieve also, and the precision at K that it's in our project, what we focus on, since at the end, if it's an e-commerce, you want that you retrieve the most relevant results at the first page, so the client can see the first results as the most relevant, and they bought what is similar and they get it as soon as possible. Also, we have used our database. I will talk about the datasets now, but we use real world images to evaluate that the system is working well. So about the datasets, we use two datasets. One that is our database, in fact, that is the fashion product images dataset. This is, as you can see, a very homogeneous dataset with very centered images with background in white. So it's real images. These are not are this. So we want to first of all build a system that works with this type of images, but we decided to evaluate also with real world images and see if we can improve our system to achieve the best results that we can with the time we had. So also about computational requirements, our plan was to use our personal machine with an NVIDIA GPU and also Colab and Google Cloud, but at the end we didn't get time to deploy correctly in the server, and we decided to continue with our personal computer, and at the end we achieved several trainings. So I think that we have had enough computer resources to perform this project. Finally, we also built the project and deployed it with Docker. That was one of our objectives. So we have used these technologies to create our models.
The milestone. These are the milestones that we had proposed. There are group in MVP. The first is to have a minimum functional system, and we have achieved it. You can see it in the presentation. And the MVP 2 is the optimization or fine-tuning. We have also achieved it, but we think that this never ends. If we had more weeks, we continue with this task. And the MVP 3 is the deployment. We have deployed the application inside the Docker container, but it isn't available in the cloud. We decided with the team and with Kevin, the advisor, prioritize the improvement or fine-tuning part before the implementation on cloud. For this reason, we have added this extra milestone, not considered at the beginning. The dataset that initially was planned has to evaluate, at the end has used it to train our best model. You can see in the experiments slides. And the project plan, we would like to show a comparison of the predicted plan versus the executed one. In light purple, you see what was predicted. In dark purple, what is done within the plan, and in the dark orange, what is done outside of the prediction. Regarding tasks outside the prediction, just to point out that we have realized creating evaluation model and fine-tune can be the task that never ends. We are happy with our final results, but for sure we will continue with them if we have extra time. On the other hand, the task to adapt the pre-trained models to our objective has been faster than we expected. And now we will explain the results.
Yes. So we have divided into different experiments, and it's actually what we have done time to time. And the first thing that we have done is a pre-trained model. So the hypothesis for this first experiment was basically to find the best model that would work for our specific use case, the retrieval engine. And we decided to use this list of models that we got also, as I think the previous team, from this Torch Vision models library. And we basically in the beginning knew that most likely VGG, ResNet, and DenseNet would be the ones that behave the best because of, almost for in every paper that we checked, and also from our advisor, from Kevin, these would be the ones that were the best for our use case. Basically what we also try to do is to build a system, so in the backend itself, that would be able to easily change from one model to another, because we wanted to check these pre-trained models with different ones. We decided to separate it in with different responsibilities, so it would be easier to work with it. Then we decided at the end to include these 6 models, as we see, because since we prepared the code to easily change from one model to another, it was just very easy to include one more. And we wanted to make the full comparison. As you can see, what we have included as input is these normalized features. So once we pre-train the models for the evaluation, we use these 2 different systems that are called the mean average precision and the precision hits. As Ferran mentioned before, the one that is more valuable for us is the precision hits, because what it does is actually sorted by the score of how well it predicted the feature in a top 15, in our case, is the one that we use. So this is the one that is more interesting for us, because at the end, the output of our system is this top 10, top 15. As you can see, as we expected, the models that behaved the better were DenseNet, VGG, and ResNet. However, the last thing that we wanted to do to proceed with the next experiment was to check with a real world image. Also, as Ferran showed you before, the dataset that we used was very similar to, like, the images were very good, or how to say, like with the white background, and also very focused on the specific load that it was. So we wanted to test it on real one. We saw that it was not behaving as good. As you can see here, the precisions are really, really high. So we were getting great results, but for the real data, not. So as a result of this experiment, we decided to customize the models to see if we could improve it like that. So as next experiment, we focus more on DenseNet 161, but as I told you before, since we already had the whole backend prepared to work with different models, we took the opportunity to also check some others. So for us, what it means customized. So it's actually using transfer learning, and also freezing most of the layers and training some others to check if we can, with this, improve the results of our retrieval engine. We decided to start training very few layers, because what we saw is that if the more layers that we unfroze, the more overfit we would get if we trained too much, because at the end the data set was also not very varied, with a lot of variety. But as you see, also here the input is with normalized features. I'm sorry, something that I didn't mention is that we used a special set of data for testing, one for training, one for validation, and one for testing. And although we have 44K images in this dataset, we use these 5K images for the evaluation. So as you can see, as conclusions, the precision improved significantly, and also the mean average precision. And here also you can see the confusion matrix and the TSNE. That is something that we saw in one of the last trainings. Yeah, you can see that it's very, very focused on it. It's getting the features very accurately. Again, we check it in real images, but it was still not behaving really well. So this lead us to the next experiment that Jordi will explain.
Thank you. The experiment 3 is a custom model with fine-tuned PCA. For features extracted from the models, we perform a post-processing that consists of the normalization and a reduction of dimensionality. To reduce the dimensionality, we use the PCA technique. The hypothesis is if we reduce the dimensionality and remove redundant and unweighted data, maybe the models improve. In the first experiment, we used a fixed dimensionality for all models equal to 128. We have created a process that evaluates the different possibilities of PCA based on 2 metrics and choose the best dimension. The metrics are the MVP, the same, the mean MVP is the popular metric, and the precision hits that explained it Melania. And I can be seen from the results. The conclusion is that the model improved, especially the MAP metric. In the table on column used features appears a key features. It's average query expansion features. It's a technique used to calculate the new features and consists in replace the features of each image by average of the topK rank results, including the query image itself. We believe that the best dimensional obtained is not high because the images are simple with a white background and they are scented like e-commerce products. And the experiment 4, evaluation with deep fashion. In the previous experiments, we have tested the models with images from the dataset itself. We want to see the results when we use images that are not from the dataset. To do this, we have adapted another dataset, deep fashion, with images with backgrounds or people with clouds, which we think are more closer to real images. We have worked the data and joined the types of articles from one dataset and the other, with the same levels. We have also need to adapt the evaluation functions, for example, the ground truth matrix calculation. And the conclusion is that when realistic images are evaluated, the precision decreases significantly. And Ferran explained the next experiment.
Yes, after that, we decided that we want to use more data to make our trainings more heterogeneous, so our model is not as based as in our database images that are white background. So the first hypothesis that we performed after that was that we need something that makes our model know about real images. And we decided to use a first technique that is the batch normalization, that it's not a training, but it's just try to pass the data over the model and not back propagating. So the batch norm statistics are fine-tuned for the new data. This is done for the pre-trained models in the first experiment, and works well, since the other models are trained with different data that it's not and it's not about our data. But in this case, the results, instead of being better, it was not good. So as we can see, the TSNA makes the clustering worse, and also we decreased a lot in all the metrics that are relevant for us. And that happens evaluating with the fashion product, even with the deep fashion. Then we decided to try another thing, that it's trying to create our deep fashion model. So using the deep fashion data only, and from using from scratch the DenseNet 161, that was the one that we decided that it's the best in from now. We try to train the model as a classifier, and finding with the new data set and with the mappings that we done from one levels from one data set to the other, a new model that improves, does not improve when we evaluate with fashion product, but it's in the average, in the precision hits. But we get a best accuracy at top 50 with deep fashion images. That it's normal because we use deep fashion to get this model. And so we obtain the best model that we have with real world data to the top precision. But in the other hand, we don't have a good map that also is a relevant metric in a retrieval system. So after that, we decided that we need to use both data sets at the same time to train our model. So we based our training on a pre-trained custom model, and then training with the deep fashion data. After that, we didn't get good results again. So this was very strange, but we arrived to these results very late, and we investigated because it was very suspicious that after doing these experiments, we didn't reach better results. So after that, and the confusion matrix, testing with the accuracy with the testing data set of the deep fashion, it gives an accuracy of 0.7, that it's not bad, but after testing, the precision hit was very low yet. So after that, and investigating, we detected that it was an error when encoding the data levels in both sides. So it doesn't match, and of course the model, instead of learning, it was forgetting what it knows from the other. And well, but we reached this point as the last experiment, and we didn't have time to continue solving this problem and taking the best results.
And quickly, the diagram final solution. I don't have time, but I explained the diagram of the solution, and it's the result of what explained above, and at the end, all is connected. I mean, it's a solution to modify and add new improvements, and these improvements or change are directly reflected into the results of the model and the front end. So everything is completely connected. And for presentation, we have divided to scheme to parts because it's very hard. But you can see the full scheme on GitHub. And on the left is the preparation part with 2 different data sets, and we generate the train and validation. And the right is the training process, because with different training methods. It's the normalization and the scratch or transfer learning method. In the next slide, On the left is the class models, is the class of the pre-trained models, and on one side transform every different model to a feature extractor, and the other side transform each model for train, adapt layers, adapt number of classes, freeze, unfreeze layers, etc. On the right is the feature extractor process, and we generate 4 checkpoints. One is the model checkpoint, and another is the 3 different types of features what we generate. In the next slide, on the left is the fine-tune PCA, and the right is the evaluation process. In the next slide is the process that display or learned features in a 2D space using TSNE. And now Ferran.
And then we also depicted here how it works, the frontend and the API module. And at the end, we have the retrieval engine that it makes use of all the data before, that features manager, the model manager. We deploy it in Docker and also use Docker Compose to build the full solution and also execute it for a demo. So we can see here a couple of GIFs that the application is working. So this is a couple of examples of queries. And then the conclusion.
Yeah. So now the conclusions, for general conclusions very quickly. So we have seen that DenseNet 161 is the best model also when applying this transfer learning, so freezing the layers and training the others. The precision hit for our specific use case is the best evaluation metric. The fine-tuning of PCA improved significantly the results, and also, yeah, we realized that for our specific data set, the PCA was also very small, so the features that were giving us the most information were few. The use of AQE is especially useful when we already have a good precision hits because of what Jordi explained before. It's getting the top features, the best features from the training to use them. The use of dataset with real-world images makes the model missing important features, I guess, without real-world images, sorry. And when using a dataset that is simple, this I think I already mentioned, the important features is very low. Fine-tune, it's very important, but also very time-consuming. Future work, we wanted to mention because with this project we learned a lot and we know that we know nothing. So we could apply these visualizations for units in the last convolutional layer. This is something that we learned in some of the last class. The class activation map, also very related to the previous method, where you can see in actually the image where are the main characteristics that your model is getting. Occlusion, it's a different system that by hiding different parts of the image would make the neural network focus on different parts of the image. Test time data augmentation. So although we're using pretty large data sets, we realized that not for all of the classes we had a large number of different images. So data augmentation can help on this. Graph diffusion, back of local convolutional and silence weighting. This is something that Kevin suggested to us, also because I think he's working on this kind of papers. And then regional features and fine-tune with using triple loss also can help a lot. Thank you.
Perfect. If you want, we can do a little demo.
Maybe I'll take a look because we are those times. Yeah,
the application working, and well, you select an image. For example, we have fashion images, external or fashion product. If we use a fashion product, that it's one of our
I'm sorry,
database.
we're a bit out of time. I'll take a look. I'll probably deploy it locally, I'm afraid. Yeah.
Okay.
Okay. Thank you for the presentation. I'm sorry, because we don't have time.
Good.
Yeah, so thank you very much. I pointed some things. So yeah, first of all, I really like the approach you did to evaluate, like evaluating with real world images, because you could have totally just taken the simple data set and evaluated with that, and it would have looked a lot better. But yeah, you did that, which is very good, like using more real looking images. So that's very nice. I'm curious, I don't think you mentioned, or maybe I missed it. So once you extracted the features, let's say in inference, how do you find the closest images?
Yes, we use Jordi.
No, we use the cosine similarity.
Cosine similarity, and you do the cosine similarity with all the images you have in your dataset.
Yeah.
Isn't that so?
Yeah.
No,
I
not
think.
much.
No. We. Sorry, Ferran. You?
Yeah. Well, we have like 44K images, but it's not very slow. It's consuming like